Hi, this is Sonia Doucette. For this video, I'll show you how to calculate the pH of a buffer solution containing an acid and also a salt containing the conjugate base of that acid when a strong acid is added. The problem asks you to find the pH of a 0.150 liter buffer solution, that is 0.25 molar ascorbic acid and 0.20 molar potassium ascorbate, after 0.0050 moles of hydrochloric acid have been added. So hydrochloric acid is a strong acid, and when a strong acid is added to a weak acid solution, ascorbic acid being the weak acid in this case, a neutralization reaction occurs. In this case, the conjugate base of the weak acid, which is the ascorbate anion C6H7O6, is neutralized by the hydronium ion that comes from the addition of hydrochloric acid. So the ascorbate anion is present because when potassium ascorbate dissociates in solution, you get a potassium ion plus the ascorbate anion. And when hydrochloric acid is added to solution, you get a proton and the chloride anion. And the proton does not hang around on its own for very long because it's very reactive. It reacts with a water molecule to give you the hydronium ion. So the neutralization, again, that occurs here is between the ascorbate anion that's coming from the potassium ascorbate and the hydronium cation that's coming from the hydrochloric acid. So this neutralization reaction looks like this. You have your hydronium ion plus your ascorbate anion, and the hydronium ion donates a proton to ascorbate to give you water, which is what's left over after the hydronium ion donates its proton, and ascorbic acid, which is what that ascorbate anion becomes once it receives one proton from the hydronium ion. So you use this reaction to, and this should actually be an arrow pointing one way, and that's because when neutralization reactions involve a strong acid such as hydrochloric acid, they pretty much go to completion, meaning you're left with almost 100% products and very, very little reactant. So you can use this neutralization reaction to create a table, and this is not an ice table. This is a different kind of table where you have three rows. You have the moles of each species present before neutralization, the moles, how the moles change during the neutralization reaction, and the moles of each species present after the neutralization reaction has occurred. So to fill in these rows, you need to know the moles of all of the species present. So let's fill in the before row first. For moles of hydronium ion, we're given that 0.0050 moles of hydrochloric acid are added. And because there's a 1-to-1 molar ratio between hydrochloric acid and the hydronium cation, if we have 0.0050 moles of hydrochloric acid, we also have 0.0050 moles of hydronium ion. So we can write 0.0050 for the moles of hydronium ion before the neutralization reaction occurs. For moles of ascorbate anion, we need to do a calculation to find the moles. So we're given that the volume of this solution is 1.50 liters, and we're also told the molarity of potassium ascorbate, which is 0.20 molar. So the molar ratio between potassium ascorbate and the ascorbate anion in the balanced equation describing the dissociation of potassium ascorbate is 1:1. And because it's 1:1, if we have 0.20 molar potassium ascorbate, we also have 0.20 molar ascorbate anion. So we can say multiply the volume by 0.20 moles per liter. And when you do the math there, you end up with 0.03 moles of ascorbate anion present before the neutralization reaction is carried out. You can also find the moles of ascorbic acid in a similar fashion. So you take the total volume of the solution, which you're given, and you multiply that by the concentration of ascorbic acid, which you're told is 0.25 molar. So we have 0.25 moles per liter of ascorbic acid. You multiply and you get 0.0375 moles of ascorbic acid present initially before the neutralization reaction occurs. So you filled in your first row of this table. The next thing you want to do is subtract 0.0050 from both of the reactants, because for every mole of hydrochloric acid added, you get 1 mole of hydronium ion, and for every mole of hydronium ion that reacts, you're going to lose those hydronium ions, but also lose 1 mole of ascorbate anion. So you subtract the 0.0050 from the reactant side and you add it to the product side, because for every mole of hydronium ion that reacts and that you lose, you will gain 1 mole of ascorbic acid. So you add it to the product side. And then all you have to do is subtract this number from reactants, so you get 0.025 and 0.0425. So remember, what we're trying to find here is pH, and to do this, we can find the hydronium ion concentration using the equilibrium expression, or the Ka value, for ascorbic acid, and also the concentration of ascorbate anion and the ascorbic acid concentration. And this is all after neutralization, so we're focused on the last row of this table. So in order to find the concentration, because we only have the moles right now, so to find the concentration of ascorbic acid and the ascorbate anion, you can divide by the volume that you're given. So you're given that the buffer solution has a volume of 0.150 liters. So dividing moles by liter gives you moles per liter. That's molarity, that's concentration. So assuming that the solution volume remains the same as 0.150 liters after the addition of hydrochloric acid, so adding that hydrochloric acid does not change the volume, that's what you're assuming, you can say that your ascorbate anion concentration is going to be equal to 0.025 moles. So this is what you found to be the number of moles of ascorbate anion remaining after the neutralization reaction. You're dividing by your known volume of 0.150 liters. Do the math, you get a volume of 0.1667 molar. You can also get the concentration of ascorbic acid in the same way. So you take the moles of ascorbic acid remaining after the neutralization reaction is complete, so you have 0.0425 moles of ascorbic acid. You divide that by 0.150 liters of total solution, and you get 0.2833 molar for your volume of ascorbic acid. So after this neutralization reaction has occurred, the principal proton transfer reaction that's occurring in solution is proton transfer from ascorbic acid to water to give the hydronium ion plus the ascorbate anion. And this reaction also occurs in the reverse direction. The equilibrium equation that describes this reaction and the equation that we can use to solve for the hydronium ion concentration is Ka is equal to the hydronium ion multiplied by the ascorbate anion concentrations divided by the ascorbic acid concentration. So we've solved for the ascorbate anion concentration, we've solved for the ascorbic acid concentration. We know the Ka value for ascorbic acid. We can look that up, and it is equal to 8.0 times 10 to the negative 5. The only thing we don't know is the hydronium ion concentration. So we can rearrange this equation to solve for the hydronium ion concentration. So the hydronium ion concentration is equal to Ka times the ascorbic acid concentration divided by the ascorbate anion concentration. Substituting in our known values, the Ka value for ascorbic acid is 8.0 times 10 to the negative 5. The concentration of ascorbic acid that we've solved for is 1.667, so this was the number we just solved for up here. And then we have the concentration of ascorbate anion, which we solved for as 0.2833. So here's our value from here. And now all we have to do is do the math to find the hydronium ion concentration, which is equal to 4.7059 times 10 to the negative 5. The final thing you need to do is find the pH, which is equal to the negative log of the hydronium ion concentration. So substituting this value that you just found for hydronium ion concentration into this equation, and you will find the pH is equal to 4.35. So you solve for pH, that's all you have to do, and you're finished.